we'll slowly build up towards some of the functions that we have looked at before. Okay, so here's the first example. So suppose you have a sequence. So this is usually sequences given by recurrence relations. So suppose I give you the following recurrence relation. So I say that, so I have a sequence of numbers A0, A1, A2, and so on. So I tell you the value of A0, A0 is 0, and AN plus 1 is given to be 2AN plus 1. Okay? This is for all n greater than or equal to 0. So what this determines is a sequence AN, and goes from 0 to infinity. And this initial condition together with this recurrence is enough to tell us what the sequence looks like. So for example, what are the first few terms of the sequence? So A0 is of course 1, A0 is 0, A1 is 1 because it's 2A0 plus 1. But what are the next 5 terms? Compute
3.
Compute it fast and tell me. 3,
7, 15, 31, 62, sorry, 63.
Okay, fine. So let's see. We have enough terms to already make a guess as to what this looks like. So what is the nth term? Suppose I ask you for a formula for the nth term just by studying this pattern. So what does AN look like?
2 times AN minus 1.
Times AN minus 1 plus.
That's right, but that is my recurrence relation. See, that is what's already given. But what I want is some function of n. Should
So 2 power 2 power n into A naught plus, that is plus 1.
Sorry,
okay,
what?
Okay.
Minus 1.
Okay, wonderful. 2 power n minus 1. So notice that it's just 1 less than powers of 2, right? So, I mean, we just have to slightly ensure that the starting values match correctly. See, for example, A0, 2 power 0 is 1. So 2 power 0 minus 1 is exactly A0. Okay, so now this formula is just a formula in terms of n. Okay, and this is true now for all values of n greater than or equal to 0. Okay, and in fact, there are ways of sort of proving that this is what the answer is. For example, what's the most obvious way to prove that this is the answer? So we want to prove this formula. I mean, this is at the moment just given by observation, right? We're just observing the pattern and saying this is what it must be. But if we want a proper formal proof, then given this data, you can only start with what's given.
By induction.
Induction, wonderful. So that's what you do, right? So induction on n is the most obvious way to proceed. You will just assume that this is the formula for, I mean, it's of course true for n equal to 0. Assume that it's true until n even, and then use the given recurrence to show that the induction, use the inductive hypothesis and the recurrence relation to find the value of the next guy. So for example, so let me just quickly show you. So I'm going to assume the induction hypothesis will be AN is 2 to the n minus 1. From this, we must check that AN plus 1 also has the correct form. But AN plus 1 is 2AN plus 1. So that's 2 times 2 to the n minus 1 plus 1. And if you simplify that, that's exactly 2 to the n plus 1. Okay. I think we should just, sorry, just a second. We'll disable screen sharing, disable annotation. Okay, so let's look at, so the induction hypothesis says AN is 2 to the n minus 1, and now this formula tells me that an plus 1 is 2 to the n plus 1 minus 1. Okay, so okay. Now, so that's the proof by induction. Okay, but what we now want to do is to try and do this by a different method, which is the method of generating functions. So the idea here is the following: you sort of study the entire sequence in one shot. Okay, so one doesn't look at the things term by term. So you somehow want to study all of them together. Now, how does one do that? Well, you form what's called the generating function of this sequence, which is the following object, and so on. Square root 4. Okay, so this is, so in other words, I'm forming the sum an x power n. So what sort of object is this really? So x is a variable. Okay, so what sort of object is this an x power n summation? What would you say it is?
It's a series.
Right, it's a series. So it's a what sort of series? Power series, right?
Power series.
Yeah. So one way of saying it, describing what this is, it's like a power series. But for us, we will think of this as well, really only a formal power series. Okay, so maybe I will come back to this word formal afterwards. But for now, we've sort of seen power series, and this is, you know, they give you expansions of a function about a point and so on. So this is like a power series in the variable x. Okay, so let's call this series something. So I'll call it capital A of x. Okay, now here's the point. So what's the use of having constructed this sort of power series? We have a recurrence relation, right? So I know the following. I know that an plus 1 is 2 times an plus 1. Okay, and this is true for all n greater than or equal to 0. Now, this recurrence relation among the coefficients translates into a certain property for the power series. Okay, so let us see what, how would you derive the corresponding power series recurrence, if you wish. So here's the thing. Let's multiply both sides of this equation by x power n. Okay, x is some formal variable. I just multiplied both sides of this equation by x power n. Of course, this is valid, still valid for all n greater than or equal to 0. And now I will sum both sides. Since this equation is true for all n greater than or equal to 0, I can sum the left-hand side for n going from 0 to infinity. And I can sum the right-hand side n going from 0 to infinity. Okay. Now let's look at what we have gotten on the right-hand side. Well, we have to look at both sides really. So let's look at the right-hand side first. Okay. So the first term, summation n going from 0 to infinity of 2an x power n, what is that in terms of this original power series a of x?
2 times a of x.
Just 2 times a of x. Okay. And this second term, summation x power n going from 0 to infinity, what does that remind you of?
Over 1 minus x.
It's geometric series.
It's the geometric series, right? It's the geometric series 1 over 1 minus x. And well, that's...
but provided mod x should be less than.
Wonderful. Okay, good. So if you're thinking of this as a geometric series, which means that you're thinking of it actually as x is some real number, you're going to plug in real numbers for x, then you can only do this, rewrite this summation x power n as 1 over 1 minus x in the region mod x less than 1. Okay? And also true for complex numbers x if you wish. Okay, fine. So that's, maybe that's for now the right way to think about it. It's a function of x, which is valid. This replacement is valid provided mod x is less than 1. Okay, but I'll come back and tell you something about this word formal, which basically means we don't need to worry about things like this. Okay, we are not really thinking of these in terms of functions. But for now, let's do this. So by the way, this point of view is also important. It's not like we can just completely throw it out. There are instances where, especially when you want to estimate, when you want to look at asymptotics, various things like that, there this wanting to think of it as actual functions and proper power series and so on. There are occasions where you would want to do that as well. But for now, let's not worry about it. So, okay, so I replaced the right-hand side at least. Now let's go back and look at the left-hand side. So what is the left-hand side? This is the summation a n plus 1 x power n. So what does this look like?
X into a of x.
X into a of x. Is that okay? That's okay. Correct. Let's see. Let me just rewrite this and see what this is. This is so you're claiming this is x into a of x. Is that right? What is x into a of x?
A naught minus
a naught minus. So it's, I mean, your thought process is sort of right. It's shifting things by 1, but x into a of x will be the wrong shift, meaning x this is a n x to the n plus 1. That is what x times a of x will be, right? But this is not that, it's the other shift.
Derivative of x by a of x.
I'm sorry, what?
A of x by x.
A of x divided by x. Okay, fine. So observe, I need
derivative of a of x.
Derivative of a of x. So these are all very good suggestions. So the derivative of a of x also shifts powers of x down by 1, but it does something else which we don't want, which is it puts an n in front of the variable as well, right? In fact, taken from 1 to infinity, there's an extra n there which we don't have in this case, right? So that's not quite what it is. It's really a of x divided by x, right? You have to remove 1 power of x from all the terms. So let's just say this is a of x divided by x, except there's this constant term is a problem, no? So maybe the most correct way of saying this would be to say, take a of x, the original series. From that, you remove the constant term, okay, so that everything now has x and higher powers, and then divide the answer by x. This is really what we are doing when we are shifting it in the other direction, okay? But in this particular case, we also knew what a0 was, right? You were given something that a0 was 0, okay? So therefore, here it just becomes a of x by x. Okay, wonderful. So now the original recurrence relation, when re-expressed in terms of this a of x, becomes the following equation. So a of x by x, that's the left-hand side, is 2ax plus 1 over 1 minus x. Okay, so I've got all my terms. Okay, now let's solve for a of x from here. So it says a of x into 1 by x minus 2 is 1 over 1 minus x. So what is a of x finally? Can someone simplify this?
X over 1 minus x into 1 minus 2x.
X over 1 minus x into 1 minus 2x. Absolutely. Thank you. So this is the final answer. Okay. So, well, what do we mean by the final answer? See, we wanted to find a formula for the coefficients an. Instead, we packaged all the coefficients together into one single power series, one single function, and we have determined what that function is. Okay. So in some sense, we have done what was required, except we still don't really have a proper formula for an from here. Okay, so I mean, for many purposes, this is already the final answer, and you can do many other things with it. But let's see how we can find ans from here. Okay, so what do we need to do? We
Doing
need
partial fraction, there is
absolutely. Okay, great. So let's do partial fractions. Okay, so let's try to simplify it a little bit. We finally need to re-expand this in terms of a power series. That's all. Okay, I mean, broadly the answer is take this function of x and expand this into a power series about the origin. It's like taking the Taylor series of this function if you wish, but it's easier to do it using partial fraction. So let's do that. So x over 1 minus x into 1 minus 2x. So what is that? The two things. So recall, this is what one does for partial fractions, right? You would say it's sum a by this plus sum b by this, and then you can find a and b by, well, what's the easiest way to find a and b?
First multiply 1 minus x into 1 minus 2x both side, and then substitute x equal to 1.
Wonderful. So multiply both sides by the denominator, 1 minus x into 1 minus 2x, and then substitute x equals 1 or substitute x equals half to get the other coefficient. Okay, so the usual method. So can someone tell me what the answers will be?
A should be minus 1.
Okay, b.
B should be 1 by 2.
B should be
1 by 2.
1 by 2 or 2?
No. If substitute x equal to 1 by 2, a term cancel, we get 1 minus 1 by 2. B into 1 minus 1 by 2.
Left side we are having 1.
B into 1 minus 1 by 2. So what is B?
B is 1.
B is 1. Sorry, wait, let's see. I didn't quite understand. So if I have A over 1 minus x plus B over 1 minus 2x. So now what I'm saying, you multiply both sides by this. So 1 minus 2x plus B into 1 minus x. But then the left side is an x.
B is 1.
B is, sorry, what is substituting for x? It is half, no?
Yes, 1 by 2.
Okay.
Yeah, it's 1. 1 by 2, 1 by 2 cancel, we get 1.
1 by 2, 1 by 2 cancel, you get 1. Okay, wonderful. Is that right?
Yes.
Does it look okay now? Okay, correct. So, okay, so now let us see. So this is the final answer. A is minus 1, B is 1. And now, well, are we in better shape? Well, yes, because we know how to write the power series for these two functions, right? These are not just a geometric series again. So the first term is minus summation x power n. Second term is just the summation 2x whole power n. Right? I've just again written the geometric series, and if you wish, this is valid. First one is valid when mod x is less than 1. Second one is valid when mod 2x is less than 1. So both are definitely valid when mod 2x is less than 1, meaning mod x is less than half. Okay, and what does that give you? Exactly what we expected, right? So now I've simplified the power series, and I've discovered that the coefficient of x power n in this power series is exactly 2 power n minus 1. Okay, and recall the left hand side, which is ax, was exactly a n x power n. Okay, so what does this tell us? It tells you that a n is just 2 power n minus 1. Okay, is this fine? Any questions on any of the things we have done? So this is one approach to finding solutions to recurrences. So
in general, if the two power series are equal, we cannot say the coefficients are equal, right?
Okay. Why not?
That is uniformly convergent, and we can say.
Okay. See, if you have power series and you compare two power series within their radius of convergence, right? So inside the ball, see, or I don't know, you want to think in terms of complex numbers, maybe then around the origin in the complex plane, if I expand two functions, and if the power series are equal, then they're equal coefficient by coefficient. Okay, because they uniformly converge and all the nice properties are there. Okay, so but I mean that's exactly the sort of worry you should be having right now, because we started out wanting to do combinatorics, trying to count some stuff, and then along the way this whole generating function thing seems to have introduced some sort of analytic objects, right? So suddenly we are doing analysis in the middle of discrete math, and so then the worry is really, are we doing things right? There is convergence, there is comparison of power series, etc., etc. And so let me make some remarks about the adjective formal that I used. So what we are actually doing in this example and all these various counting by generating function examples, what we'll do is we will consider what are called formal power series. Okay, so what are formal power series, if you wish? So, well, they're just formal in the sense of, so you just take the collection of, so let me say formal power series with complex coefficients. Okay, so what is a formal power series? It's just a formal sum like this, okay, where all the AIs are complex numbers. Now, what can I do with formal? So, okay, so this is, in other words, a formal power series is just another name for an infinite sequence, right? It's got the same information, A0, A1, A2, and so on. Now, so this is a formal power series, and we usually call the collection of all formal power series as C double bracket X. Is usually called the ring of formal power series with complex coefficients. Okay, what does this have? This has all these possible formal power series. The elements are exactly all these guys. Okay, so two formal power series are equal if and only if their coefficients are the same. Okay, so the elements of this set are, just think of it, if you want it to be even more rigorous, maybe you can say formal power series are just infinite sequences of complex numbers. So if you really want to be very pedantic about it, you would probably say what I'm looking at is the ring whose elements are infinite sequences of complex numbers, A0, A1, A2, A3, and so on. So of course, two sequences are considered equal only if they agree in all the terms. Okay. Now, of course, it's not very convenient to think of it in terms of sequences, but rather as power series, because we want to look at multiplication of power series. That's the point. Okay, so we want to think of it really as a ring with addition and multiplication. So here are some operations you can perform on power series. If I take two of them, I can add them by just in the obvious fashion. I can just say this is A0 plus B0 plus, and so on. Okay, so it's an infinite sum. The right hand side is again some formal power series, right? Or if you want to think in terms of sequences, I'm saying take two sequences, you add them up by adding up the corresponding terms. Okay, but the real thing is with multiplication. That's the key point somehow. A0 plus A1x plus A2x square and so on. You define multiplication of two formal power series. Again, the way you would define multiplication for polynomials, for example, which is to say the constant term is A0, B0. The coefficient of x is A0, B1 plus A1, B0. Coefficient of x square is a sum of three terms, A1, B1 plus A2, B0, and so on. So this will have four terms, A0, B3 plus. Okay. Now this is see what I've done on the right is actually just defined the product. If you give me two infinite sequences of A's and B's, I'm telling you how to form their so-called product, which is the elements of, if you want to say it's again a sequence, an infinite sequence, then the elements of that sequence are A0, B0, then A0, B1 plus A1, B0, then the next guy, then the next one, and so on. So I'm telling you how each element of this sequence is formed. I'm giving you a rule to form those elements in terms of the A's and the B's. Okay. Of course, it's modeled on how polynomials or our usual analytic power series behave. But at the moment, it's completely formal in the sense I'm telling you this into this is defined as this is the following summation Cn x power n, where Cn is defined as follows, where C0 is this guy, C1 is this formula, C2 is this formula, and so on. Okay. Now this when I say this is formal, in fact you can see that all this works very generally. In the sense, suppose I take R. Let's say R is any commutative ring. Okay. So you can take, instead of the complex numbers, I can take the ring of integers, for example, or more general rings which are commutative. So if R is a commutative ring, which means that I know how to add and multiply elements of R. That's all I know. Then there is something that I can define called the ring of formal power series with coefficients in R. Okay. What is this guy? Well, I just copy the same definition. I say I take all such objects, the elements look like A0 plus A1x and so on. The A's come from the underlying ring R. And then how do I multiply, or how do I add? Add is easy, component wise. How do I multiply? Well, this is my rule for multiplication. Okay, I just give you the rule. Okay, and observe that this makes perfect sense over any ring R, because after all, A0, B0 must be defined, and it should be another element of my ring R. So this guy again is another element of R, right? Because it's a sum of products of elements of R. Similarly, this will certainly be another element of R, and so on. So the product of power series with coefficients in R will turn out again to be an element of R of x. And of course, the thing with making such formal definitions is that you have to prove all its properties. Okay, and that's where the sort of the painful part is. If you define it like this term by term, then you must show that all the various properties hold. Okay, and that becomes rather unnatural. So when you're doing this, thinking of power series as functions and so on, then it's obvious, because so for example, I claim that this product that I've just defined on power series is associative. This is an associative product. Okay, how do I prove this? If I'm thinking of them as functions, there's nothing to it. It's obvious that the product is associative, because it's just like I'm multiplying the values of the function. If I have fx, gx, hx, I'm going to say fx into gx versus gx into hx, and so on, right? But here, because it's all formally defined, what you'll have to do is to go through the definitions and show that if I take this power series A of x, which is sum a n x power n, and then multiply that by bx cx, okay, that gives me the same answer as first multiplying a and b, then multiplying the answer by my formal power series c of x. Okay, but it can be done. It's not so hard to do, and if you sort of see what you get in the end, you'll find that both these answers will work out to be the same as power series b of x. So by the way, I'm just using shorthand for this is the power series b n x power n, c n x power n. So this final answer is nothing but, so what I'm saying is, you'll actually have to do this verification, but at the end it'll be easy, because you'll find that both these products, both these orders will give you the power series d of x. So where d of x is summation dn x power n, where the coefficient dn will turn out to be the following. It's summation ai bj ck, where you have to run I, j, k over all ordered triples, with sum up to n. Okay, you'll when you do this, you'll find this what you get. Okay? And this is now associative in the sense you first do B, C, and then you do it with A, or you do A, B, and C. In both cases, you'll end up with the same answer, and that's how you show associativity. Okay, so so the point I'm trying to make here is that you can make such a formal definition as what we just did, right? Purely with just coefficients coming from some ring, and everything is fine. It's just that when you start trying to prove the properties, then you have to be careful and ensure that all the properties are proved properly using the definitions. Okay, but you know it's rather remarkable and beautiful that all our usual properties are actually true in this ring. Okay, so let me show you an instance of this. So let's go back to our power series ring C of X. Okay, so what is this power series ring? This is just formal infinite power series. Whose coefficients are complex numbers, and on which multiplication is defined the way I just defined it. Okay, so let me define two polynomials, two elements of this ring, two power series. So first I'll define x to the n, and let me define gx is 1 minus x. Okay, 1 minus x is a polynomial. It doesn't have coefficients beyond x square, but that's still an element of this ring, right? So this is a formal power series. This is also a formal power series. Okay. Now let's check the way we define this multiplication formally. What is fx into gx? Let's just do the calculation. So this is 1 plus x square plus and so on. And gx is just 1 minus x. So let me do it slowly, term by term. Okay, so first let me compute in fx gx what's the constant term. My definition was I have to multiply the two constant terms together. So this is a 1 plus coefficient of x is constant term of the first guy multiplied by coefficient of x of the second guy plus coefficient of x of the second guy times constant term of the first guy, a0 b1 plus a1 b0. So I do that. Here I get 1 into minus 1 plus 1 into 1. That's the coefficient of x. Okay, coefficient of x squared similarly will be a constant term, which is 1 times the coefficient of x squared in the other guy. There is no coefficient of x squared here. So it's 1 into 0 plus coefficient of x here into coefficient of x there. So it's 1 into minus 1 plus coefficient of x squared into coefficient of 1. So that's 1 into 1. And so on. So when I try, you know, at the moment I'm doing it carefully to say that I'm using my definitions. So then similarly it is 1 for the next guy, 1 into 0 plus 1 into 0 plus 1 into minus 1 plus 1 into 1, x cubed, and so on. Okay. Any questions on what I just did? I'm just using the definition carefully. That's all. Each term I'm just computing what is it in this example. So what will we get here?
1.
So what's the coefficient of x? This is a 0, right? So this is 0 times x plus next is, well, again a 0 and so on. Okay, so you'll see that every term has, well, it's got a bunch of zeros and then there is a minus 1 and a 1. Okay, so what does that mean? It says that in this formal power series ring, this power series and this power series, when you multiply them together, you get the power series 1. Okay, and 1 is actually the multiplicative unit of this ring. If you multiply 1 by anything, you just get back that same thing. So it says, therefore, that these two fellows, f and g, they are multiplicative inverses in this ring. C of x, f and g are just multiplicative inverses. And what does that mean? Well, whenever I see f, I can replace it by the inverse of g, right? I can say So when I write 1 by g, I just mean multiplicative inverse of g. Okay, so f is 1 by g. So by this I just mean multiplicative inverse. In this ring. And that's exactly what we mean by saying this power series x power n goes from 0 to infinity, is 1 over 1 minus x. Right? This is the, so all along originally we are used to thinking of this as an identity which says, think of x as a real number. And when mod x is less than 1, the left hand side converges, gives you gives me a number, and that number turns out to be the same as the number 1 over 1 minus x. Okay, also, like Anamali pointed out, this converges uniformly if you take any any compact set less than any interval that's strictly within 0, 1, minus 1, 1, and so on. So you can think like that. You can talk in terms of convergence and how it defines a function of x and so on and so forth. But notice that we have just completely thrown all that out. For us, x is just some formal indeterminate which is used to form this ring of power series. And this identity here written in this way is only saying this left hand side is an element of the power series ring. This denominator 1 minus x is an element of the power series ring. And when I multiply them both in the power series ring using the definition of multiplication, the answer comes out to be a 1. Okay, so this is the multiplicative inverse of that in this power series ring. That's all we are saying. Okay, so we have sort of converted all this back into algebra in some sense. So there's no more analysis. We're just thinking of this as some computations in this power series ring. Okay, any questions on this? Okay, so let's do one more just to get a hang of how this goes. So suppose I have a slightly harder recurrence. So this is so they say an plus 1 is 2an plus n rather than plus 1. Okay, so this is n greater than or equal to 0. And suppose I take my first term is 1 as before. Okay, and again you can compute because this recurrence will uniquely determine my sequence. So what will my first few terms look like? It's 1, next term is 2 times 1 plus n 0, right? 2 times 1 plus 0, so that's 2. 4 plus 2 is 4 plus 1, sorry, a1. 4 plus 1 is 5. 10 plus 1, no, 10 plus 2 now, 12. 24 plus 3, 27. And I have to multiply that by 2, 54 plus 4, 58. 116 plus 5, 121, and so on. Okay, so all I've done is just taken the same recurrence and now try to work out what the first few terms look like. Again, I mean, you can try and see what this might be, maybe by the pattern and so on. But since we've sort of worked out this method of generating functions, let's just apply it and see what we get. So I'm going to just call a of x to be this power series summation a and x power n. And now let's say, okay, all this is in my formal power series ring. Okay, it's just thought of as an infinite sequence. So then let us, what does the given identity say? It says that a n plus 1, so let me do this, x to the n is 2an xn plus n xn. Okay, this is true for all n greater than or equal to 0. Okay, so this is what I know because of the given recurrence. So I just think of this, the power series, which is n goes to 0 to infinity an plus 1 xn, is the same as this formal power series plus this formal power series. Okay, because remember, how do you add formal power series? You just add them coefficient by coefficient. Okay, and this is telling you that the coefficient of the left hand side power series is equal to the coefficient of the first power series on the right plus the coefficient of the second power series on the right. Okay, so at the moment what I have written is a correct equation inside this ring of formal power series. This is how I add two formal power series. And now let's see what are these. We've just done this sort of thing before. This first term is 2ax. The term on the left is just ax minus a0 divided by x. Okay. Now, I mean, there's maybe some slight issue with this whole division by x on the left, on the right, because you may say, what does this division by x mean? Because I don't know what I mean. See, I'm sort of saying, oh, all the stuff I'm doing here is taking place inside this formal power series ring. Now, what does this 1 by x represent? Right? So that's a legitimate worry. So the question already here is, what do I mean by the power series 1 by x? In other words, is there, so what should this mean? This should mean this is the multiplicative inverse, right? So what is 1 by x? I can claim, oh, it's that power series h of x, which is the multiplicative inverse, satisfying the following property. H of x into x gives me 1. Okay? H is some power series, h naught plus h on x and so on. Okay. Now, all this multiplication is to be done inside this power series ring. So can this ever be true? If I take a power series h like this and I multiply it by the power series x, is there any chance I can get 1?
No, the constant term is not equal.
Correct. So notice that the constant term is not hx into x. The constant term is already the constant term is 0 on this side. The left-hand side is going to look like this, h naught x, and so on. The right-hand side is a constant power series 1. It's got no other terms. Right? There's no chance these two things can ever be equal. So in fact, 1 by x is not an invertible element of this ring. I mean, x is not an invertible element of this ring. There is no such thing called 1 by x. Okay? X is not invertible, doesn't have a unit in this ring. Okay? So these are all nice things to keep in mind, because I mean, these are, if you thought of the function x, then of course you could say, oh, I can find its inverse provided x is not 0, right? But inside my formal power series ring, I can't do that. Just from what I just showed you, you cannot find a formal power series h which serves as the multiplicative inverse. Okay, so maybe this is not, this is slightly unsatisfactory. We don't want to be dividing by x and so on. We want to somehow only do operations which are legal inside this formal power series ring. So let's just make the following change. So let me this is also valid. So I'm going to multiply both sides of my so I mean I can just say, consider the formal power series an plus 1 x to the n plus 1, and that is equal to 2an x to the n plus 1 plus summation n x to the n plus 1. Okay, so this is again true. This is because the original thing was true for all n greater than or equal to 0. I'm just sort of slightly modifying my power series. Okay, so I want to consider this power series, which begins the power of x in it. The smallest power of x is x power 1. The same thing here. The smallest power of x starts from x to the 1. This again starts from x to the 1. Okay. Now, so again, this equation is true. Okay, because again, how do you add power series? I've just changed everything by x, right? Moved everything by x. Again, addition is the same. I just add component by component. But now, at least I can think of these as valid elements inside my power series ring. So what is this fellow here? An plus 1 x to the n plus 1.
A of x minus a naught.
Wonderful. So now observe, there is no division by x involved. This is just a of x minus a naught. That's all. Okay. That's the reason why I did this. Okay. So I can think of this as a of x minus a naught, because If I put n equal to 0, it starts as a1 x power 1. So let's look at the next fellow. What is this?
2x ax.
Observe, this is 2x ax, absolutely. Plus, now coming to this term, what does this look like? Right, this was suggested before. Maybe we should take the derivative, because that's exactly the sort of thing which will bring an n in front of the terms, right? So let's do that. So let me see, what does this start with? It starts with x power 1. So this is x. So let me pull out an x. Think of it as n x to the n. Okay. So of course, if n is 0, this is just 0, right? So I have to, let me massage the terms a little bit. Observe that in this term, if n is 0, then this is that particular sum is 0. So I'll just put n from 1 to infinity. That's enough. And now let me pull out x square. So this is now n goes from 1 to infinity. And then I pull out x square from all the terms and make the inside nx to the n minus 1. Okay. So I've done nothing. I've just realized that this will only start from x square and higher terms, because n has to be at least 1 for this to give me a non-zero coefficient. So I pulled that x square out and I looked at what's left. So now I run into this series. So I need to understand what is the series summation n x to power series ring C of x, right? The coefficients are n's for x to the n minus 1. But can I write this in more compact form? Just like I realized that summation x power n is just 1 over 1 minus x. So I know this. Okay, so this is a compact form of the left-hand side of the series. Similarly, what do I get for nx to the n minus 1? Okay, so let's again, be a little analytic. Think again in terms of analysis. If you actually had a function whose power series was known, so for example, this equation here, 1 over 1 minus x is summation x power n. So recall, you can term by term differentiate power series, right? So if I take the left-hand side function and I compute its derivative, okay, just the usual, remember this identity here expresses something about a function between minus 1 and 1, right? 1 over 1 minus x is a function in this interval whose value is the same as the value of the right-hand side, summation x power n, where x is, you have to assume x is something between minus 1 and 1. Okay, so because they're functions, they're in fact very nice functions, I can differentiate any number of times and so on. So I take the derivative of the left-hand side, that equals the term by term derivative of the power series. So this is one of the theorems one learns about power series, right? That you can do term by term differentiation. So what does this give you? It's nx to the n minus 1, and the left-hand side is the derivative of 1 over 1 minus x, which is minus 1 over 1 minus x the whole square. Right?
Minus.
Is there a minus?
Yeah.
1 over 1 minus x is minus 1 over 1, but there's one more minus from here, no? See, am I doing the same? So the chain rule will mean that I also have to put one more minus from. So it's minus 1 over 1 minus x square, but then there's a minus 1 in front of the x. So I should get plus 1 over 1 minus x square. Is that all right?
Yes.
Okay. So now the claim is that, well, actually the same thing is true in the power series ring. So I claim that this, in the formal power series ring, nx to the n minus 1 turns out to be exactly the same as 1 over 1 minus x the whole square. Okay, what does that mean? So I claim this holds. in this formal power series ring. In other words, if I define my function f of x to be 1 minus x the whole square, and if I take g of x to be summation n x to the n minus 1, then when I multiply them in my formal power series ring, I claim I will get a 1. Okay, let's check this. Okay, so what is this? It's 1 minus 2x plus x squared. Okay, and this is just summation nx to the n minus 1. So how does one multiply these two polynomials in the power series ring? Let's multiply them out. 1 minus 2x plus x squared. And this is nx to the n minus 1, right? So this is 1 times x to the 0, 2 times x to the 1, and so on. So I have to multiply them and see what my coefficients will look like. So in general, what's the most general sort of computation? So observe at some point it will be k x to the k minus 1. There will be a k plus 1 and a k plus 2. K plus 1 and so on. Okay, so let me just look at these three terms alone. I mean, those three will be the only terms which will come up when I try to compute the coefficient of x to the k plus 1. Okay, so observe coefficient of x to the k plus 1 in this product will only come from three contributions. So one, I have to take this k plus 2 and multiply it by this 1. Okay, so that's k plus 2. So x to the k plus 1 into 1. X to the k into x. So that's minus 2 into k plus 1. Okay, and then finally k times x squared. So that's plus k. So there are only these three contributions. Okay, and observe that's exactly 0. Okay, so all the coefficient of x to the k plus 1s, terms in the middle when k is at least a 1. Okay, so this is all 0. Once k is sort of at least, so I don't know what, at least 2 or at least 1. X to the k plus 1. Okay, let's just do the first few terms just to ensure things are okay. So constant 1 into 1, give me a 1. Then minus 2x.
So we can directly multiply.
That's already a 0. Correct. So plus 0 times x. Correct. That's, yeah, all I was trying to do was sort of tell you what the most general multiplication will look like. But you're right. Maybe it's better for intuition to just do it directly. So 1 into 3. So this will be 3 minus 4 plus 1 x squared. And so on. Right. So 3 then will be 4. 4, 3, 2. So those will be two guys. So 4 and then 2 times 3 plus 2. And so on. So if you see sort of term by term, just like we did in the previous computation, every other term will just vanish. You'll just get a 1. Okay. So what does the thing mean? It just says that the summation nx to the n minus 1 inside this power series ring, formal power series ring, is nothing but the multiplicative inverse of 1 minus x the whole square. Okay, so I mean the very same analytic fact, it'll often be true when you sort of do it in terms of the formal power series also. So in fact, one can define a formal derivative on power series and show that the formal derivative has the similar properties as a usual derivative, like the product rule, things like that. Okay, so one can sort of develop a parallel theory of formal power series. Okay, but let me not get too much into this. So I just want to see how. So I'm just telling you all this to say that what we are doing is not really analysis. You don't need to think in terms of analysis. Though these notions of derivative and so on are all being used here, they are all the corresponding formal variables. Okay, so let's get the final answer in this case. So where did we? Where were we? We said.
Yeah.
Sorry. This one, right? This was my question. So let me replace this x square into 1 minus x the whole square. Okay, so that is my equation now. Ax minus a naught is this. So let's copy that. Now let's simplify it. So here's the equation. A naught was, this case, what did we say? 1, right? A naught was also given. A naught was 1. So this is my equation. This means that Ax into 1 minus 2x is x square by 1 minus x the whole square plus 1. What's that? That's let's see, it's x squared plus 1 minus 2. So 1 minus 2x plus 2x squared by 1 minus x the whole square. Okay, I probably don't need to do all this. I already have it in the form I want. So this implies that a of x is just 1 over 1 minus 2x plus x squared over 1 minus x the whole square into 1 minus 2x. Okay, so I have a formula for ax. I can simplify it further if I want. But again, how does one determine the explicit formula for ax, for the ans? Okay, so as before, let's do partial fraction. So let's take this guy and split it further into partial fractions. So one term is already sort of come out. So we'll keep it as it is, split the other one. So how does that split into partial fractions? Well, you have to do more terms, 1 minus x the whole square. We recall it's b over 1 minus x plus c over 1 minus 2x. Okay, so what does one do then? You figure out what are the values of a, b, and c. Okay, so I'm sort of going to leave it at this point as an exercise for our tutorial on Sunday. So please do try this, determine the values of a, b, c, and then like last time, like in the first problem, expand. Once you know the values of a, b, c, you can just write out the power series of each of these terms using either the geometric series or for 1 over 1 minus x square, we already know the formula and so on. And using that, actually find out a formula for an. An equals, I want some function of n. Okay, let's find out what this function is. So please try it, and we'll do it during the tutorial. Okay. So let me move on now to something that's that we talked about during I guess during the last lecture, which is the notion of the Stirling numbers. Okay, and recall here that this came up when we said, okay, we have the various kinds of problems. You try to put balls in boxes, but then there are you can either take identical balls or identical boxes and so on, and each of them gives rise to a different problem, right? And we said maybe the two difficult problems which don't have easy answers are the set partition problem and just the usual integer partition problems. Okay, so let's look at recall what the set partition problem was. So here, what are you doing? You're putting labeled balls. That is, the balls have some numbers on them, but you're putting them into identical boxes. Okay, the boxes you don't care in which order they are arranged or whatever it is. And this corresponds to saying I have a set. For example, let's say I have a set of 4 elements, 1, 2, 3, 4, and I then want to partition this into some k subsets. Okay, and I don't care, how I write the subsets, whether I write one of them first, 1, 2 first, and then 3, 4, or 3, 4, and 1, 2, and so on. I only want to keep track of which numbers are together inside one subset, right? Who are all the numbers which form a group together? Okay, and that's all I want to remember, right? Who are all neighbors of which numbers. Okay, so for example, so then we define this number. So I said SNK is the number of set partitions of 1 to n into exactly k subsets. Okay, so let's do an example. So let's just look at what is S of n comma 4, 2. So by which we mean I want to partition this set 1, 2, 3, 4 that I just wrote out. I want to partition it into 2 subsets. Okay, so what are all ways of doing it? So I can take 1, 2, and 3, 4. So let's write the 2 partitions like this. 1, 2 is one partition, 3, 4 is the second partition. Or let's rewrite this. So this is my first way of doing it. What's another way? I can write 1, 3 together, 2, 4 together. Okay, I can write 1, 4 together, 2, 3 together. Okay, so these are the only 3 ways of doing it if I want to split it as 2 and 2. Okay, but there are other things I can do. So let's take a 4th method, which is I take 1 separately and then 2, 3, 4 together. 2 is by itself. 1, 3, 4. 1, 2, 4. 1, 2, 3. Okay, so I have 7 ways of doing this. What else can I do? Anything else I can do? Doesn't look like it, right? I can either split it as 2 and 1 or 1 and 3. So I have all the possibilities. So what is S42 is exactly 7. There are 7 ways of partitioning the set 1, 2, 3, 4 into 2 subsets which are disjoint and whose union is everything, such that, I mean, without worrying about the order of the subsets and so on. Okay, now let's see how one can use generating functions to determine these numbers. So I mentioned that there is no easy way of saying what these are. You cannot get them by using our binomial coefficients, all this divider and so on. Those methods don't work because the boxes are indistinguishable, and that's a somewhat more difficult thing to somehow capture. So let's do this using generating functions. Okay. Now, so let us see. So I've defined this S and K. For what values of n and k are these defined? Well, K is now a number between, I suppose, n is at least 1. K is a number between 1 and n. So for this range of values, this S and K makes sense. Okay. So we'll soon want to also define it for some other values. So maybe we should also say that. So how shall we define S and K for these things which are outside the bounds? So so suppose K is too large. So if K is bigger than n, okay. So maybe I should just write all this into one single place. So S and K is this, provided so this is the usual definition, and for things which are outside my range, so let's just like this. So this is the standard range, and things outside the range, if I want to define it as 0. So what does outside the range mean? If either K is too big, K is bigger than n, of course I cannot partition the set 1 to n into k non-empty subsets, or what are the other bad things I don't want? If n is negative. Okay, this is like defining binomial coefficients for these negative values and so on, right? So let me put some additional constraints. Or if k is negative, for example, in all those cases, I will just define S and K to be 0. Okay, and the one thing that I have not defined is what happens if n equal to 0. So if n equal to 0, in other words, I sort of have a set with 0 elements. that is the empty set, and I want to partition the empty set into some number of subsets. So it's sort of a vacuous thing there again. So maybe for 0 again, let's just make a definition. So this is just one additional convention if you wish. Okay, so let me just tell you what the convention is for 0. So in this case, I'll just put further. Okay, so S of n comma 0.
0, okay.
S of n comma 0, I will want to put as 0, right? If n is at least 1, meaning if I have a non-empty subset, I cannot partition it into 0, into a union of 0 subsets. At least one of the subsets, I should have at least one subset. So this is also fine, logical. And the only thing we have missed out in all of this is how do you define S00? Okay, and that we define as 1. Okay, so I mean, at the moment, you can think of these as just some conventions. The only values of n and k for which it truly makes sense is this thing in the middle, right, where it has an actual meaning. It is the number of partitions of the set. All the others that I have written out are maybe you can think of them as conventions. Okay, but somehow they are the most logical values that you might want to give, except for this. Right? This is like saying y is 0 factorial 1, for example. Right? That there's no real logical way of proving that, but that's somehow the convenient choice which will make the formulas much more natural and compact. So you really want to make your life simple. Pick the thing which will make the final answer nice. Okay, so that's, if you want, you can redefine it, but then your answer finally will just also change by whatever you redefine. Okay, so these are all conventions. If you will. This is a convention, and this thing here is a convention, and the thing in the middle is really the definition that makes sense. Okay, so I have defined these numbers S and K now for all integers n and k. Right? So observe what this finally does for us is S and K has now been defined for all integers n and k. Positive, negative, 0, everything. Okay, now
So what about S of 0, comma k?
That is from here, right? If k is greater than 0, right, 0 comma k, if k is greater than 0, then this condition tells me that
Okay.
it is 0. If k is negative, then this condition tells me it is 0. So 0, 0 is the only one that's not yet, that's not inside the earlier ones, and that you define as 1. Okay, so this is just a bunch of conventions, the rest of it. But the real thing comes now. So let's actually work out what the recurrence relation is. What recurrence relation do these S's satisfy? And here's the very interesting recurrence relation. So suppose I take S and K. And for this, just think about the usual standard domain of definition. If K and N, so N is at least 1, K is a number between 1 and N. Usual sets being partitioned into K blocks. So what can I say about S and K? So recall we had a similar recurrence for the binomial coefficients. If I had to say what is NCK, we said, okay, let's take how many ways to combine, how many ways to choose K fellows. Let's assume one fellow is chosen or that one fellow is not chosen, right? And that gave you a split into 2 pieces. Right? So this was the recurrence for the binomial coefficients. Now something similar actually works in this case, okay, which is the following. What does S and K mean? It says take the numbers 1 to n, dot till n, and try and partition it into K blocks, right? I'm supposed to partition this into K blocks. So the number of ways of doing it is my value S and K. Okay, now again, just like in that binomial theorem example, let's focus on one single fellow, okay, which is in this case, let me take the number n. So let me see, among these partitions into K subsets, let's look at those partitions in which n occurs as a singleton. Okay. N occurs inside a sub, occurs as a singleton subset. Okay. So this partition has one of its blocks is just N itself. Okay. So let's see how many will there be like that. And the other kind, which is the partitions in which N occurs together with some other numbers. Okay. N is alone, N is not alone. Those are the two cases we look at. Okay, first case, N occurs alone. So let's ask, how many partitions will have N occurring alone? How will I determine this? Keep this in mind. This is
S of
N
minus 1 comma k.
Okay, S
S
of
of n minus 1 comma k.
N minus 1 comma
K minus 1.
K minus 1.
K.
Right? Because one block is singleton
No.
N. Right? One block is the singleton
Yes,
N.
sir.
And then K minus 1 blocks in the remaining. Right? So that's exactly like this. Okay, now we had to be slightly more careful here. Let's do this. N is not alone. So N occurs as part of a block containing other numbers. So suppose I delete N now. I take this partition in which N doesn't occur alone, and suppose I delete N from that partition. What am I left with?
So N minus 1 points.
Okay.
Then you have to choose K partition.
I'm left only with N minus. Okay, I'm left with N minus 1 points, and what I obtain is a partition of that set of N minus 1 points into K blocks, right? Because the number of blocks doesn't decrease. I have deleted N, but N is not alone. It is part of a block containing other numbers. So the other numbers will survive, right? But this is not quite correct. I mean, this is not the formula. Snk is Sn minus 1 K minus 1 plus Sn minus 1 K is not the formula. There is a certain amount of overcounting which is sort of happening in this second term here. Okay, why? Because, so observe, if my original partition was 1, 2, 3, 4, 5, okay, and maybe 5 occurred together with the 4, okay. So if I delete the 5, what I'm going to be left with is 1, 2, 3, and 4, right? So this is what I will get. But what if 5 occurred in the other partition? Suppose this was my original partition, 1, 2, 3, 5, and 4. Okay. Now when I delete the 5, what do I get? So here are 2 partitions of the set of 5 elements. In both of them, 5 is not alone. But when I delete 5 from each of them, I end up with the same partition of 1, 2, 3, 4. Okay. So what does that mean? It says that there is a certain amount of overcounting that I get. Okay. So the extent of overcounting is the following. Maybe not overcounting. What I should say is undercounting. The partition 1, 2, 3, 4. That's what is being counted by this, right? This is the number of partitions of 1 to 4. But from that, to get a partition of 1 to 5, I can put the 5 together with, I can put that 5 in any one of the blocks. Okay. In whichever block I put, I will get a new partition when I put it in the different blocks. So from a single partition of 4 guys, I will actually be able to generate K partitions of 1 through 5. And what is K here? K is the number of blocks. So is this final argument clear? So what I'm saying is imagine I have a certain partition of 1 to 4, and now from this I want to construct a partition of 1 to 5. I can put the 5 either here and get a certain partition, or I can put the 5 here and get a new partition. Okay, those are going to give me 2 different ways, 2 different partitions of 1 through 5. In both of which 5 is not alone, and on deletion of 5, they will both give me the same partition of 1 through 4. Okay, so it's a slightly difficult argument if you haven't seen things like this before. So maybe I would encourage people to think about this a little bit more and see how one gets this. Okay, but having gotten this, that this is really the recurrence. Now, what one can do is, solve this recurrence in much the same way that we solved the earlier ones. Okay, so this is true for all n greater than, like I said, for all n greater than or equal to 1, and for all k between 1 and n. But in fact, what you must check is that actually this is true for all nk in Z, except for 0, 0. Okay, 0, 0 alone, remember we defined it differently. If nk is 0, 0, S0, 0, the left hand side will be 1. So except for nk equal to 0, 0. Okay. For 0, 0, the left hand side is 1 and the right hand side is a 0. Okay. So other than that case, or for all other choices of n and k, this recurrence is actually true. Okay. Why? Because of the convention. It will always be 0. Both sides will turn out to be 0 if you are outside this proper region of definition. Okay. So that's something to check here. But what I want to point out is how one solves this recurrence. Okay. So let's use generating functions again. Now, the way we do this, the generating function. So there are many different ways of proceeding because this is actually a two variable. See, we actually have two parameters n and k, right? So when I form the generating function, which one should I really look at? Should I fix n and think of it as being summed over k, or should I fix k and sum over n? Turns out it's easier to do it if you fix k and sum over n. Okay, so let me just do that. So a of x, I will define it as follows. Look at the formal power series, the Stirling number S and k into x power n, and now n ranges from 0 to infinity. Okay, so this is my definition, and now I will see how this recurrence relation translates into a recurrence for this a of x. So let's look at both sides of this recurrence relation again. So we call S and k is S n minus 1 k minus 1 plus k times S n minus 1 k. Okay. Now again we'll do the usual thing. We'll multiply both sides. So summation x power n Okay, and now what does this give me? This says that, sorry, what does this give me? This gives, oh, sorry, I should have said something. Remember, I'm fixing k here. Okay, so a k of x is being fixed in this formula, and this, okay, there are some initial conditions. A0 of x is just only S0, 0 is going to survive. So A0 of x is 1. Okay, so that I know. So now let me just see what this equation implies. So the left hand side is exactly A of x. S and k x power n is A of x. The second term is, sorry, is A k of x. Second term is A k minus 1 of x. But then there's an x that I can pull out from this, because this is an n minus 1 here. I put an n minus 1 and an x in front. Okay, so plus, same thing, summation. The next term again is a. So this is ak. Again, I'll pull out an x. So it's ak of x into ak of x into kx. Okay, so again, I'm just doing the same thing as before, which is I pull out an x from, so I write it as kx into Sn minus 1 k x power n minus 1, so that the summation becomes ak of x, basically. So now what does this mean? This tells me that ak into 1 minus kx equals x times ak minus 1 of x. Okay, and this is actually true if k is at least 1 in this case. So this equation again, this is if k is at least 1. Okay, and for k equal to 0, I sort of know what my answer is. Okay, so now we are almost there. So this tells me that ak of x is the same as x over 1 minus kx into ak minus 1 of x. Okay, that was my formula. Okay, and now you can see that this is like a recurrence relation again. So this is for k at least 1, and I know that a0 is 1. So now I'm ready to relog what all the things look like. A0 is 1, a1. This is a 1. A1 of x is, I use this relation on top. It says it is x over 1 minus x times a0. So that's what it is. A2 is x over 1 minus 2x times the previous answer. So it's x squared by 1 minus x, 1 minus 2x. A3 of x is x cubed by 1 minus x, 1 minus 2x, 1 minus 3x, and so on. Okay, and we keep going, and we sort of make this rather remarkable final observation that this is, I can actually tell you what the Stirling number is. What is it? Well, it is just form the following generating function. I mean, look at the following function of x. X power k divided by 1 minus x, 1 minus 2x, 1 minus kx. Okay, and the Stirling number, so remember this by definition was just s n k x power n. Therefore, final conclusion is that the Stirling number s n k is nothing but the coefficient of x to the n in this answer, whatever this looks like. Okay, so again, this is, I mean, you can more or less stop there and say, well, I have determined what the Stirling number is, because information about all the Stirling numbers, all the SNKs, is actually contained in a very compact form inside this function of x. Okay, this single compact form of the function, this nice form, it's just a rational function. This contains information about all the SNKs. Okay, and I mean, you can take that point of view, but if you say, no, I really want a formula for SNK in terms of n and k, then all you have to do is just do partial fractions to this expression here. Okay, so maybe that's again something which we will defer to the tutorial. So partial fractions for this expression, okay, will give a formula. Okay, and it's actually a very nice formula. So again, I encourage everyone to sort of try it out in advance before the Sunday tutorial. It's a very beautiful formula. So remember, this is interesting. You have to do partial fraction with so many terms, k terms, but still it's no harder than with 2 terms and so on. So the final answer is very, very beautiful. Okay, so what we will do in the tutorial is certainly work out a explicit formula for the Stirling number. Okay, but the overall point of today's lecture really was the following. See, we said this set partition problem is difficult, right? And a very nice formula is not, finally we still don't have a too nice a formula maybe, but the generating functions is it's a very powerful sort of tool, and it all hinges on this recurrence relation here. So even though SNK is difficult to understand, we can get a recurrence relation for SNK. See, the NCKs are easier to understand. One point of view is because they have an easy recurrence. The recurrence that connects NCK to n-1 CK is this rather easy sort of recurrence. And that leads to an easy formula for the NCKs. That's the reason why they are, maybe simpler if you wish. But from this point of view that we are taking, the SNKs are really no different. They also obey a recurrence very similar to the NCKs. Okay, it's just that this presence of this k here, okay, if that k were a 1, then you would really be in that's like your NCK. SNK is really like your N choose K, where that recurrence relation had a slightly different coefficient. It had a K in front rather than a 1, right? So observe, if it were a 1, then you are dealing exactly with the NCKs. And so, in some sense, that's all the difference there is. That makes this other guy much more complicated. But broadly speaking, it's still the same sort of method of generating functions will work. If you actually write everything out, you'll get x to the k by this fraction. So here's another question for the tutorial. What if we had decided to do this method for the binomial coefficients? So instead of for the SNKs, I start with this. I start with NCK. I form a series C of x equals summation NCK x power n. N goes from 0 to infinity. So I fix k. Ck of x is summation NCK x power n. Then question is, use the same idea that we used for the Stirling numbers and figure out what C of x is as a rational function in x. Okay, and then do partial fractions and see that you get exactly our usual easy formula for C of x. Okay, so I guess I should stop. It's almost 7 o'clock. Since again it's my last lecture, I should end by thanking Guruswamy, Professor Radha, and others at Mepco for this opportunity, and all of you for being patient listeners. Thank you, and Happy New Year to everyone.
Thank you, sir. Thank you, sir. Happy New Year to you, sir.
Thank you, sir.
Happy New Year, sir.
So if there are any
Thank you for
questions
your
right now, I
wonderful
can take
lecture,
it.
sir.
Otherwise, I can, we can do it in the tutorial on Sunday.
So we can think other ways. Suppose if you want to find S of 5, 3. We can take all the partition of 5, but the number of terms should be 3.
Correct. Yes.
And then we have to take the number of permutation. Suppose if we take S of 5, 3.
Okay.
What are the partitions containing 3 terms is 1, 2, 2. And then 1, 1, 3, and so
on.
Partition of 5 contains 3 terms.
Partition of 5. Okay.
And then suppose if we take 1, 1, 2, 2, and we have to find the number of permutation of cycle length is the number of permutation product of 1 cycle into 2 cycle into again 2 cycles.
No. This is not the Stirling. No, this particular thing I'm talking about is the Stirling number of the second kind, which is not the cycles. So this is just set partitions.
Yeah. Anyway, both will get same answer, right?
No. You won't get the same answer for the permutations. The Stirling number of the first kind has a slightly different.
So once we get the permutation, we can make the set.
That's true, but you can't go in the other order, right? I mean, there are many different permutations which will give you the same set, right?
Yeah.
So what you're trying is to do it with permutations instead of set partitions. So that is Stirling number of the first kind rather than second kind. And again, it's part of the same thing. Instead of k, that has n here. That's all the differences. Stirling number of the first kind will turn out to be same sort of recurrence, except instead of k being this coefficient, you just have to put the coefficient n. And when you do that, it will become the Stirling number of the first kind. Okay. Again, you have to argue by similar methods. If n is not alone in a cycle, how many different cycle decompositions of n minus 1, or rather starting with the cycle decomposition of an n minus 1 permutation, in how many different ways can I put an n to get a cycle decomposition of something of n? Okay, so you have to argue like that. So again, it's a similar sort of, the final answer and the final method is the same. So somehow the nice thing with all this is there is only one method. At the end of the day, you don't have to keep doing different things for different problems. Once you decide to do generating functions, the basic method or the basic skill tool set, whatever you're using is just the same thing in every instance. But depending on the problem, the coefficients and things like that may vary, right? So if you're doing ordinary combinations, this number is 1. If you're doing Stirling number of first kind, it's every case you sort of proceed in the same way. You try to convert this recurrence relation into some property of the function finally. Right? This is the eventual goal. Try to get a formula like this. And once you have a formula, then of course you will have to, use partial fractions or whatever it is to get an explicit formula in terms of it.
Okay.
Yeah. Any other questions or comments?
So what is the need of we take complex number? So actually we always get an integer coefficient.
Yes, correct, absolutely. So I'm not doing any complex numbers anywhere. You're right. I could have just said, let's take z of x. Yeah, all of this action is taking place inside z of x. So sometimes we may need rational coefficients. So there are some instances where you need rational coefficients. So, so instance, if you take the power series e power x, that comes up in, so these are called exponential generating functions. So instead of taking the summation, so suppose I had a sequence an, then so far we are forming the power series like this. It's summation an x power n. But there's so this is sometimes called the ordinary generating function of, so it's usually called OGF, or ordinary generating function of the sequence an. But there are instances where it's more advantageous to look at the exponential generating function of an. And maybe this will come up during the tutorial, because the Stirling numbers sort of naturally fall into this category. So there's something called the exponential generating function, which is the following. You take an x power n by n factorial. So, this is sort of supposed to remind you of the exponential function. If all the ans are 1, okay, so if the an is just a sequence of ones, then the ordinary generating function, as we saw, is the geometric series. The exponential generating function is just the exponential, is e to the x. Okay, for this particular example. So there are many instances where you want to do this. And so, like you say, maybe the rational functions are sufficient. It's enough to take formal power series with rational coefficients, because these would certainly be rational numbers in general. Yeah, we don't really need complex numbers. Okay, so maybe we can stop and talk more about this on the tutorial on Sunday.
Okay, sir. Thank you, sir.
Yeah, thank you.
Sir. Thank you.
Thank you, sir.
Thank you.
Happy New Year, sir.
Sure.
Yeah,
Happy New Year.
You
sir.
too. Yes.
Thank you. Thank you, sir.
Thank you.
Thank you.
Thank you, participants. Wish you all have a happy New Year.
Thank you, ma'am. Thank you. Thank you.
Okay, sir.
Thank you, ma'am.